Yes, hello students. In today's lecture, we shall discuss the single phase fully controlled rectifier fed separately excited DC motor. So here I have shown here a bridge rectifier and it is supplying a separately excited DC motor. Field winding I have not shown here. So it is only armature which I have shown here. The field winding is given a constant voltage DC supply. So the flux is constant. So let us first review how this single phase full wave rectifier works. Now there are two pairs of thyristors T1 and T3 and here T2 and T4. So at a time either T1 and T3 will conduct or T2 and T4 may conduct. So what happens when T1 and T3 conduct, then the circuit completes like this. So you can say that when T1 and T3 conduct, this terminal reaches this point and this terminal reaches this point. So the output voltage, that is voltage across armature, is equal to the source voltage. And when this happens, in that case, when T1 and T3 are conducting, this terminal, suppose this is the phase terminal, this is the neutral terminal of the supply. So this terminal is P, this terminal is N when T1 and T3 are conducting. So this means that what is the voltage across the off-state thyristors? T2. So this is P and this is N. So this voltage, the anode to cathode voltage, is equal to minus Vs. So this terminal is N, this terminal is P. So VT2, that is voltage across thyristor 2, that is anode to cathode voltage, is equal to minus Vs. And similarly voltage across the thyristor T4, it is equal to VNP, that is equal to minus of Vs. So the voltage across off-state thyristors T2 and T4 is equal to negative of the source voltage, and the source current is same as the armature current. So this is a condition when T1 and T3 are conducting. On the other hand, when T2 and T4 are conducting, the other pair, in that case this terminal will be N, T2 is conducting, and this terminal will be equal to P. Now the output voltage, that is armature voltage, will be equal to negative of the source voltage. So it is equal to minus Vs. And when T2 and T4 are conducting, T1 and T3 are in the off state. In that case, the voltage here will be equal to, this is the source voltage, this is P, this is N. So Vt1 is equal to Vs. Similarly, Vt3 will also be equal to Vs. So in when T2 and T4 are conducting, Va is equal to minus Vs, Vt1 and Vt3 are equal to Vs, and source current is equal to minus of Ia. Ia flows like this through T3. So source current is equal to minus, the armature current flows through T4 like this. So this is equal to minus of Ia. So the source current will be equal to minus of Ia. Now, when all the thyristors are in the off state, that's neither T1, T3 conducting nor T2 and T4 are conducting. In that case, output voltage will be equal to the voltage across this machine, that is the back EMF. So what happens is that when you apply start firing these circuit, these thyristors, voltage appears across the armature of the DC motor starts running and it gains certain speed, and in steady state it has certain speed, and as the voltage is not a constant or fixed DC voltage, it is a variable voltage, the speed will also vary as the voltage varies. But as you know that the motor has a high inertia, high mechanical time constant, the variation in the speed of the DC motor will not be high and it will be almost ripple free. So the back EMF here will be almost ripple free depending on the average value of the voltage that appears across the DC motor. So it will not respond to the fluctuation in the armature voltage, rather it will respond to the average value of the voltage here. So this, you can say that the back EMF will be k omega m, and that will be almost ripple free. So we assume here that inertia is high enough so that the ripples in the speed is negligible, and it is a ripple free DC voltage here. Of course, if you change alpha, if you change the firing angle, the voltage will change here and the speed will decrease, change gradually and settle to a new value of speed. But in steady state, it will remain constant and ripple free. So this is the condition. This is the operation of this full wave controlled rectifier. Now there may be two possibilities of the current. Current may be continuous or it can be discontinuous. That is, when you fire the positive pair T1 and T3, current has some certain value. After certain time, current starts decreasing. I will discuss it later. Current may fall to 0 before we fire the next pair of thyristors. So during a negative cycle, the current is decreasing and it may fall to 0 before the firing of next pair of thyristors. So that will be called discontinuous conduction. And if the current doesn't fall to 0 and we fire the next pair of thyristor, then it is called continuous conduction. So let us first focus on continuous conduction. So in continuous conduction, what is the wave shape of output voltage of the thyristor of the bridge or input voltage of the DC motor? So here I have shown the equivalent circuit of the DC motor. RA is the resistance of the armature circuit, LA is the inductance of the armature circuit, and E is the back EMF. So I have shown here the voltages Vs. Vs is Vn sin omega t, it is sinusoidal voltage, and minus Vs is opposite of this. So I have shown it by blue lines here. So these two voltages are there. Depending on which pair is conducting and which pair is not conducting, output voltage will vary. Now for operation of the full wave rectifier, we give the firing pulses continuously from alpha, that is the desired firing angle, till the end of the cycle, pi plus alpha, rather alpha to pi, and the other pair, that is T2 and T4, are given the firing pulses from pi plus alpha to 2 pi. That is during positive half cycle, T1 and T3 are given firing pulses, and during negative half cycle, T2 and T4 are given firing pulses, and the starting of the pulse is delayed by the desired angle alpha, depending on what average voltage we want and what speed we want from the motor. So this is the case. So let us assume that the conduction is continuous. In that case, either T1 and T3 will conduct or T2 and T4 will conduct. So let us assume that from the previous cycle, T2 and T4 are conducting, and at this instant of time, we had given the firing pulse to the thyristors T1 and T3 simultaneously. So in the beginning, when T2 and T4 are conducting, in that case, output voltage will be equal to minus of Vs. So let us draw the waveform. So it is minus Vs. So during this interval, output voltage is equal to minus of Vs. Then at omega t, and when T2 and T4 are conducting, voltage across the thyristors T1 and T3 is equal to Vs, and you can see that Vs is positive. This means that T1 and T3 are in the forward bias state and they are not conducting because we have not given the firing pulse. We have given the firing pulse at this instant of time, and thereafter they will start conducting, and the output voltage will become equal to Vs. So after this, output voltage will become equal to Vs like this. And what happens to the voltage across the earlier conducting thyristors? As soon as we trigger T1 and T3, this situation comes. Output voltage, the voltage across thyristor T2 and T4 is equal to minus Vs, and this is negative. So as soon as we trigger T1 and T3, T2 and T4 become reverse biased, and the current flow shifts from T1 and T3 to T2 and T4. So output voltage will be equal to Vs, and it will remain Vs. And as you know that thyristors are latching devices. Once conducted, they will not turn off unless the current falls below holding current. So I will explain it later. Current will not fall to 0 here. So T1 and T3 will continue to conduct unless we fire the other pair of thyristor, and which we do here at pi plus alpha. We give the firing pulse to T2 and T4, and as soon as we do this, output voltage will become equal to minus Vs. This is minus Vs. And when T2 and T4 are conducting, voltage across T1 and T3 is equal to Vs, and Vs has become negative here, so they will turn off immediately. So as soon as we trigger T2 and T4, T3 and T1 will turn off. So output voltage will be equal to minus Vs, and it will remain so till we trigger T1, T2 again. So output voltage waveform is like this for value of alpha that I have shown in this diagram. So this is the output voltage waveform. Now, during this interval, what is the average voltage across the armature? Now you know this wave shape. You can see that the wave shape is repeating after this. So the frequency of output voltage, frequency of variation of output voltage is double the frequency of variation of the supply voltage. Supply voltage completes one cycle here, whereas the output voltage completes one cycle here. So frequency of output voltage is double the frequency of input voltage. Now let us try to find out what is the average value of the voltage that appears across the motor, because the motor's speed will depend on average value of the voltage. So you can just integrate it 1 upon pi alpha to pi plus alpha during this interval. You can take any interval for integration. One full cycle should be there. So from alpha to pi plus alpha, output voltage is equal to Vs, that is equal to Vm sin omega t. Just put the value and you will get the value here as 2 Vm by pi cos alpha. So output voltage will have average value equal to 2 Vm by pi into cos alpha. Depending on alpha, you will have certain value of average voltage. So let us indicate this average voltage here in this diagram. Let me use this color. Suppose the average voltage here is this is the value of average voltage. Average value of the voltage, that is you put the value of alpha here, it will have certain value. The back EMF will be slightly less than the average voltage. This you can apply Kirchhoff's voltage law for average values. So VA will be equal to EA will be equal to VA minus IARA. Average value of voltage across inductance in a steady state is always equal to 0. Across the inductor, the voltage becomes positive and negative depending on whether current is rising or current is decreasing, and the average value of the voltage across inductance in a steady state is always equal to 0. So EA will be equal to VA minus IARA, and this will be slightly less than VA. So let us show it here. So it will be, you can show it by red lines. So it is usually the value of R is very small. So So you can say that this drop is negligible. And one thing you must remember that this IA is a function of torque, load torque, because in a steady state the motor torque is equal to load torque, and load torque, so that the current will depend on the load torque. Higher the load torque, more will be the current. So this means that the value of EA for same VA as the load is varied will change. So for higher loads, this will be even smaller than this I have shown here. So this EA will be less than VA depending on the load on the motor. So this is now I have shown here the back EMF by this line. So let me use the symbol E here. So this is the case. Now let us see what will be the wave shape of the current, armature current. For this, let us write the KVL equation for instantaneous values. So VA is equal to RAIA plus LA di by dt plus the back EMF. This back EMF is constant. So this is an example of RLE load. So from here you can write di over dt as VA minus E upon LA. The drop in the resistance is very small and can be neglected. So let us assume that this drop is negligible. In that case, di over dt will be equal to VA minus E upon RA. VA is the instantaneous value of armature voltage. Now there are various situations you can see here. This is the wave shape of VA. For certain period of the cycle, VA is more than E. For certain period of cycle, VA is less than E. So this can be seen from here. So what are the situation here? If instantaneous armature voltage is greater than E, this means that dIA over dt will be positive. This implies that IA will increase. So during that period where VA is more than E, current will rise. So let us identify the period where the VA is more than E. So this is this interval. During this interval, the VA is more than E. So this means that during this interval, current will rise. So it will rise like this. So during this interval, current will rise. And on the other hand, if VA is less than E, this implies that dIA over dt is less than 0, which indicates that IA will be decreasing during this interval. So during the remaining period, VA is less than E and the current will be decreasing. So current will be decreasing during this interval. So like this. Again after this, VA becomes more than E, current will start increasing. Like this. So in that way, you can show the waveform of the armature current. So this is the waveform of the armature current. So during this interval, current is rising and the peak will be at this point where the decreasing voltage, armature voltage becomes equal to back EMF. And of course, when VA is equal to E, the current will be constant. So this is the zero slope point here, and again here also it is the zero slope point. So in that way you can have the current waveform. And if you want, you can show the average value of this current. So this let me show it by some other color. So let us, this is the wave shape of, or the average value of the armature current. Of course, when the load changes, the wave shape will shift downward. For example, the load decreases. This means that IA has to decrease, so the wave shape will shift downward. On the other hand, if the load increases, average value of I has to increase, the wave shape will shift upward. So that is the wave shape of the armature current. So now we can see that this is the operation of the rectifier controlled DC motor. Now, what is the flow of energy? We have to think about it. That is, whether the energy flows from source to motor, or sometimes the energy may flow from motor to source. So this we have to analyze. So I will explain it just now. Now let us see how the power flows in this circuit. You can identify different parts of the cycle here. So I have shown here that during this interval alpha and the instant when the decreasing voltage becomes equal to back EMF, that instant I have shown by gamma. So during this interval, armature voltage is more than back EMF, and the source voltage is, or the armature voltage is positive. The situation is shown like this. This is source voltage or the armature voltage. This is positive, and VA is more than E, so the current is rising, it is increasing. So DIA or DT is positive. This means that the voltage across inductor will be having this polarity. The current is flowing in the inductor resistance in this direction, higher polarity, lower polarity. So you can see here that the energy flows from source. So armature voltage is nothing but it is equal to the source voltage. So the power flows from source into the motor. A part of this power is consumed by the resistance and dissipated as heat. A part of this power will be stored in the inductance. So energy is being stored in the inductance. As the current is rising, energy stored in the inductor, half Li square will increase. So this inductance will store energy, and the remaining power will be converted into mechanical power by this motor. So during this interval, this is the flow of power. And after this gamma and till the end of the positive half cycle pi, situation is that the output voltage is greater than 0, but it is less than EA. So when VA is less than EA, current is decreasing. This means that DIA or DT has become negative. This means that the polarity of inductor voltage LA DIA or DT will be opposite to what it was earlier. So here it was plus minus, it becomes negative here and positive here. So now current is still positive, so current flows in this direction, so higher potential, lower potential here, and then polarity of inductor voltage has now reversed. So you can say that energy still comes from the source and it is partly dissipated as heat in the armature resistance, and now this inductance, it is now releasing the energy. Energy is coming out from this. So the energy that it is stored during the previous part of the cycle is now being released. So this energy is released. So you can say that during this interval, this is the source and this is also the source. So there are two sources. One is the voltage source and other is the inductor. So there are two energy sources. They are providing energy, and a part of the energy is dissipated as heat in the armature resistance, and the remaining is converted into mechanical energy by the motor. In the earlier part, this was the source and all the others were sink. RA was dissipating energy, LA was storing energy, and the motor was converting this energy into mechanical energy. Now the third part, when voltage has become negative, Vs less than 0, and of course it is less than E also, so the current is still decreasing. The polarity of inductor voltage remains same as it was here, but the source voltage is now having opposite polarity like this. The source voltage, armature voltage, which is equal to source voltage, is negative polarity here. So source voltage has reversed. So this is equal to, this is equal to Vs. So it has now reversed. Negative cycle has begun. So you can say that current still flows in the same direction. Now you can see that what are the various sources and sinks here. The current flows like this. So current, the polarity of resistor voltage is always like this, because current always flows from higher polarity to lower polarity. This means that this is the polarity of resistor voltage. So this is absorbing energy. So this is a sink. What about inductor? Energy is coming out from the positive terminal. So this inductor is behaving as a source. And what about this? This again, energy is coming into this in the positive terminal. So it is absorbing energy and converting this energy into mechanical energy. So in this case, in this part of the cycle, this is the source, and this the power source connected here is also absorbing the energy. So during this interval, energy is absorbed by the source. So the source becomes a sink. So you can say that energy stored in the inductor is released and it is sent back to the source. So this is what is known as reactive power. A part of energy which was stored in one part of the cycle is returned back to the source in the other part of the cycle. So inductor doesn't consume any energy, it rather stores energy in one part of the cycle and releases the same energy in the other part of the cycle, and at the end of the cycle the value of current remains same as it was in the beginning of the cycle. So the energy level at the two ends of the cycle is always same in steady state. So in that way this circuit behaves. So if you want to summarize, you can make a table like this. That is during the first interval, that is from omega t between alpha and gamma, the source and sink you can list here. So during this interval you can say that the armature voltage, that is the source voltage, is the source and the others are sink. So RA, LA and E, all the three are sinks. Energy is supplied by the source and consumed by these sinks. And during the other part of the cycle, between omega t, gamma and pi, the source is the voltage source Vs, and the inductor is also a source, and the sinks are RA and the back cable. And for the remaining part of the cycle, between pi and pi plus alpha, the source is inductor and this voltage source is a sink, RA is the sink and E is the sink. So in that way energy flows to and fro from source and motor. So you can say that this energy is the reactive energy, but overall this so that is during this interval it is the regeneration, that is the energy is being sent back to the source. But overall the machine behaves as a motor, and the average energy in one cycle is positive, that is the energy is flowing from source to the motor and the machine behaves as a motor. So in that way you can say that this is a motoring operation. Actually in the generating operation things will be different. So the machine behaves as a motor even though during one part of the cycle energy may flow from motor to the source. So this is a brief description of the circuit, that is the single phase fully controlled rectifier fed separately excited DC motor. So that is all for today. Thank you.